Jay Kalinani from University of Padova. So go ahead, Jay.
All right, thank you. And firstly, let me thank Professor David Radice for his very nice talk. And I probably will show slides similar to some of the plots similar to what you already talked about. And yes, this talk was supposed to be by Riccardo Ciolfi, but unfortunately he could not make it. So Andrea and I will be speaking instead of him. And we thank the organizers for accommodating this last minute change. In my talk, I'll be focusing on the recent simulations of binary neutron submergers performed with the WhiskeyMHD code and as well as our new code Spritz. And this work has been done along with Riccardo, Professor Giacomazzo, Federico Cipolletta, Wolfgang Castam, Lorenzo Naggi, and others. So needless to say, the wealth of information that was provided by the GW1708-17 event has been unprecedented, and be in terms of the gravitational waves itself or the electromagnetic counterparts, providing new constraints on the equation of state and all the Hubble constant, as well as the kilonova transient that we saw. Now, in terms of the observational data, for instance, the kilonova transient, the dynamical ejecta can solely not can alone explain, for instance, the red or the blue component of the kilonova. Hence, and we need another source, such as a massive disk that could, for instance, potentially power this red component of the kilonova. So the most likely scenario for GW1708-17 was that the merger produced a supermassive or hypermassive remnant that then eventually collapsed to a black hole. And while in this phase of the massive neutron star, it gave out ejecta, then eventually formed this disk along the black hole, forming this torus. And in nature, we also see that for instance, in short gamma ray bursts, we have these characteristic X-ray plateaus seen in their afterglows, or even these extended emissions that accompany or are part of these short gamma ray bursts. So one could argue that these plateaus could be explained by a structured jet and can be independent or agnostic of the remnant, but we cannot completely rule out a magnetar or a massive neutron star involved in such activity. And more importantly, an open question still remains that can a massive neutron star remnant power a short gamma ray burst jet? So with our merger simulations with WhiskeyMHD, we focused on this long-lived evolution of a supermassive neutron star that was formed after merger, going to time scales of about 100 to 200 milliseconds. And I think these results I've already discussed also in previous TCAN meetings, so I'll be a bit quick on this. So based on these results, we found that such a remnant can produce a very large-scale magnetic fields. And in terms of Maus outflows, we found that there are magnetically driven outflows produced by this remnant, and this outflow is more or less isotropically distributed, as you can see on this top right plot. And this is also magnetically driven or dominated, as I show this magnetic to fluid pressure ratio in the bottom. Now, this isotropic material can act as a potential obstacle for jet launching, especially because it's polluting the polar axis of the remnant. But if going up to about 250 milliseconds after merger, we also found simulations that could produce such jet-like helical structure. And in this case, there was a collimated outflow that was developed breaking out of this baryon polluted environment, reaching velocities of about 0.2 or 0.3 C. However, looking at this outflow, we found that this it's quite too heavy, at least 3 moderate magnitude orders of magnitude heavier than what is expected in, for instance, GRB 1708-17A. And the Lorentz factors, maximum achievable Lorentz factors, are by far too low, reaching less than 1.05, or what we expect is around 10. And so in these results kind of push towards magnet scenario being disfavored as a central engine for producing a short gamma ray burst jet. But our simulations did not take into account this critical role of neutrinos that which have the potential to clean up the environment along the polar axis. So for instance, on Monday we saw Professor Tokaros showed these results where with neutrinos in their simulations, this is the case with black hole and disk. So the neutrinos could clean up a little bit the environment along the polar axis. But this is again a situation where we have a black hole and we don't have a massive neutron star which could continuously produce outflows and keep polluting the environment. But on the other hand, we had the work by Moesta et al., which included neutrino effects. But what they do is they inject, or they implement, or they add a large colloidal magnetic field placed by hand later directly on the hypermassive neutron star remnant, and not so this might not be considered fully consistent, and this is still a matter of debate. So this open problem still remains to understand better how the dynamics would play between these massive outflows from the neutron star remnant and neutrinos. So my bet is on the right side, and so that probably we could have a magnetron producing jet-like structures, but this is what time will tell, and probably later simulations could address this problem. Instead, focusing on the source of the blue kilonova component, I think this was already addressed again by Professor Radice and also was talked about on Monday. So the open question still remains: what is the blue source of this blue kilonova component? And so there was one model suggested by Metzger et al., suggesting that there is these magnetally driven winds emanating from this massive neutron star remnant could potentially power this blue kilonova component. But we also have these interesting spiral density wave winds, which can be again a potential source. And why not both? So again, this is something time will tell, but in our simulations, which extend to about 250 milliseconds after merger, we analyzed these results for the ejecta velocities and the mass ejection, and we found that the ejecta velocities and the mass ejected are consistent, that is, with what is expected from a blue kilonova. Recently we introduced our new GRMHD called Spritz, and in the first version of Spritz, the Spritz is basically derived from the parent code WhiskeyMHD, and it works within the Einstein toolkit framework, and it works under the assumption of ideal MHD and is based on the flux conservative Lenscher formulation, and it assumes it evolves essentially the staggered vector potential. And the second version of Spritz also provides support for using microphysical finite temperature tabulated equations in the state, and has an implementation of a neutrino emission reabsorption in terms of a Zelmani leakage scheme. We also implemented an evolution equation for electron fraction as well as higher order methods, and Spritz is publicly available on Zenodo in case we would like to check it out. So in GRMHD codes like Spritz, we evolve the so-called conserved variables, and we need to employ root finding algorithms in order to retrieve this physical primitive variable. So recently we introduced this new scheme called Reprimand. I think Wolfgang mentioned this was introduced in Kastaun et al. 2021, and Wolfgang I think mentioned this in yesterday's discussion as well. So this essentially is based on a root bracketing method and has always shown to converge to a unique solution, and that's in general has been quite promising in terms of accuracy, efficiency, as well as robustness. And it is publicly available on Zenodo. And as well as I think it's been included in Einstein toolkit as an external library as well. So the next natural step was to implement the scheme in Spritz, and we did that, and then performed a number of demanding 3 tests in GRMHD. So on the right, you see a snapshot, for instance, of one of these tests, where we impose this dipolar magnetic field extending also outside the neutron star remnant, or neutron star, sorry, and this was a rotating neutron star case. And so yeah, here I list all the different tests that we performed with Spritz and reprimand. And for instance, on the top you have again this test where you have TOV non-rotating in this case with an external field, and we see that. And in the bottom we have the tests with the Fischer-Moncrieff accretion disk along around the black hole, which is magnetized. And in both cases, and in fact in all the tests, we found that reprimand is quite solid in terms, especially in terms of handling highly magnetized low density regions. So for the next, so using all this machinery in hand, we were ready to perform some on the first BNS simulations with Spritz using reprimand. So for our first simulations, we used the same initial data as of Ruiz et al. 2016, which is essentially a gamma equal to 2 polytopes for the initial data. And then we use the ideal gas equation of state for evolution. After about 2 orbits of evolution, we add magnetic fields to our neutron stars as dipolar fields, as you can see on the left, which are also extending outside the neutron star surface, and with the maximum strength of about 10 to the power 16 Gauss. And in addition to that, we add a co-rotating material, which goes up to about radial distance of about 950 kilometers. And this material is co-rotating with the Keplerian profile. So you see this is a rotation profile on the right. So before the material was added, this was a rotation profile of the system. But after the addition in the black, so we fit this gas with this rotation profile, this is nearly Keplerian, and then you can see after addition what kind in black is what we have the result afterwards. So this initial co-rotating system allows the magnetic field in the atmosphere to co-rotate with the system as well, and plays a role only in the beginning. Later on, when you have ejecta coming out and which goes and expands to orders of like to hundreds to kilometers, this plasma essentially plays no role, which was initially added, and it's a very low density plasma. So here on the left you see the rest mass density evolution, and on the right magnetic field evolution for this simulation. And the merger produces a hypermassive neutron star which arrives for about 8 milliseconds before collapsing to a black hole of mass of about 2.9 solar masses, surrounded by an accretion disk of about 0.06 solar mass. By the end of the simulation, which is about 50 milliseconds after merger, we find that the system has reached a steady state accretion with a disk mass of about 0.03 solar mass and accretion rate of about 0.111 solar mass per second, so which implies that the disk will be fully accreted on a timescale of about 300 milliseconds. In terms of magnetic field geometry, we see that once we add these dipolar fields, and shortly after that, they start to feel the presence of the turbulent materials and start and get distorted. And by the end of the simulation, we find that there is strong amplification along close to the equatorial plane, and also helical structures developing across this black hole spin axis. In terms of magnetic field evolution, here on the left, I show the evolution of magnetic energy. So soon after the force come into contact, Kelvin-Helmholtz instability develops in the shear layer and at a later time after collapse, magnetic winding and MRI continue to amplify the magnetic field. So by the end of the simulation, we find that the magnetic energy is still growing and is not likely enough to power a relativistic jet. And indeed, on the right top, you see the ratio of magnetic to fluid pressure, and along this funnel along the spin axis, the values are of the order of 10 to the power -4. So the funnel along this spin axis is clearly fluid pressure dominated, and on top, on the bottom right, you see the radial velocity, and red indicates essentially inflow of matter. So by the end of our simulation, we do not find any hints of relativistic jet or an incipient jet. Now, comparing our results with Ruiz et al., we find that they start with really high initial magnetic energy. So on the right, I also show a plot from Ruiz et al. 2019. And the initial energies is a little shy of about 10 to the power 50 ergs. And the corresponding initial to magnetic to fluid pressure ratio is at least 200 times higher. Moreover, they employ a much higher grid resolution. In our case, we use about 350 meters, but just before collapse, we activated a finer refinement level just to resolve the black hole. So my question also to the community is to understand how to understand better this dependence of jet formation or incipient jets on the initial magnetic energy. Do we actually need to start with at least 10 to the power 50 ergs of magnetic energy in order to find some kind of incipient jets in our simulation? Of course, for these resolutions of the order of 100, 200 meters, maybe with much higher resolution, we could even start with a lower initial energy. But for this case, are such moreover such initial strengths physically reasonable? So the alternative to such
sorry, Jay, you have about 5 minutes or 3-4 minutes remaining.
Great, thanks. So an alternative to this approach of using high initial magnetic fields is less. So this was, I think, extensively talked about in Professor Radicche's talk. So I'm just showing here some of the results from the Palenzuela paper that was discussed as well. And there's one plot on the right which shows that when you start from an initial energy of field strengths of about strengths of about 10 to the power 12, they are able to reach about 10 to the power 16 Gauss of magnetic field very soon after the KHI is, and the KHI is decently resolved. I wouldn't say fully. So, and interesting thing is that they find convergent results for this medium resolution case when the LESS is activated, and with the finest resolution is about 60 meters. When you compare, as you can see on top right, with the high resolution case, which is about using 30 meters. But again, even 60 meters for us is quite challenging. But this is definitely a promising alternative to what we're currently doing. And we would also like to implement this in Spritz at some point. But for now, since we don't have LESS in Spritz, and it was much easier just to just increase the initial magnetic energy for our simulations. So currently, for our latest runs, which are still work in progress, we are starting with different initial magnetic energies, which is of the order of almost 10 to the power 49 and almost 10 to the power 50. So and I'll show you some of the results for the simulation shown in green. And this is the magnetic energy evolution in general. So here, about 50 milliseconds after merger, we find that there is indeed some kind of outflow developing along the spin axis. And this is indeed magnetic pressure dominated. And when looking at the phenline structure, there's this is helical structure developing. And about 78 or almost 80 milliseconds after merger, we have this outflow becomes still a bit stronger and faster. And also the field, the magnetic to fluid pressure ratio also is definitely increasing and reaching orders of about 10 to a bit higher, less than 100, I would say, and close to the spin axis. But this outflow is still not relativistic in the sense that the Lorentz factors are of the order of is definitely less than 1.2. So so this is still ongoing, and focusing on other ongoing Spritz applications. We have Lorenzo Nocci, who's working on a code comparison project based on BNS simulations. He's using Spritz versus Illinois GRMHD codes. Sorry, I mentioned this as IGM. I meant Illinois GRMHD. And we have also BNS simulations ongoing with the Bielot equation of state using either Loren initial data or Kadat initial data. These are the different students of Professor Giacomazzo at the University of Milano. And we have Rahim Mathur, who is working on Again, a code comparison between Spritz and Whiskey THC using the DT2 equation state using the Kadat initial data. And in Padua, we are focusing also towards something called as end-to-end modeling. So we want to start with BNS, and this is something for the future. And we start with BNS simulations with Spritz, which are the merger happens on timescales of 10 to about 10 milliseconds and length speed of about 100 kilometers. And then we want to have jets produced. We want to produce jets, be able to produce jets on the timescale of about 100 milliseconds and length scales of about 1,000 kilometers. And then we want to port this data to another code called Pluto and performed relativistic MHD simulations of these jets and going to timescales about 1 to 2 milliseconds or even further, and reaching length scale of about 10 to the power 4, 10 to the power 5 kilometers. And Andrea will be talking more on this part, using for now just WhiskeyMHD data that we have already produced. To summarize again, for the magnetized scenario, we still we want to know the fight between this barrier pollution and the neutrino radiation, and most likely it will be resolved very soon. And for blue kilonova, we talked that could potentially be sourced by these magnetized massive neutron star winds, and also spiral wave winds are a potential option. And we now have performing BNS simulations with Spritz and reprimand, and being able to handle highly magnetized post-merger black hole disk systems. And for incipient jet formations with black hole disk systems, we have this problem that we need to start with ridiculously high initial magnetic energies for the grid resolutions that we adopt. And for future exploration, he would like to also include these finite temperature tabular equation of state, activate neutrino radiation, and also neutron star spins. With that, I stop here. Thanks a lot.
Okay, thank you very much, Jay, for this great talk. So looking at the program, the two talks are stick together. So I will ask people to write down their questions and ask them at the end of Andrea's talk, which is connected to this one. If that's okay with you, Jay.
Great, sounds perfect. Thank you.
Okay. So Andrea, do you want to
to share your screen?
Can you hear me?